Hello everybody. Today we're going to be graphing a limacon. Let me spell that out for you. Limacon. And the little C there has this little diacritical mark. It's called a cedilla, so that we know that we pronounce this with a soft C, not a hard C. If it were a hard C, that would be Limacon, which I think is some kind of convention for people who love lima beans. But with a cedilla mark, we say limacon, and in that case, we're referring to a particular type of polar graph. There's several different kinds. This is the limacon that we're going to be doing today. Okay? Now, before we even start plotting points, let's just look at this equation. One thing we notice right away is that r is a function only of sine theta. Okay, all I see on the right-hand side here are either things without sine thetas or sine thetas. There's no cosine theta, there's no theta by itself, just sine theta. This tells us something very important. This means that the graph has y-axis symmetry. Now you may be thinking, wait, we're doing a polar graph. How can there be y-axis symmetry? There's not really a y-axis. Well, we can always pretend that the y-axis is there. And anyway, the line theta is equal to pi over 2 is the same as what we think of as the y-axis. So if you want, you can think of this as having y-axis symmetry, or theta is equal to pi over 2 axis symmetry. Okay, but this is important. This tells us when we graph, every point on the right-hand side of theta is equal to pi over 2 on the graph is also going to be mirrored on the left-hand side of this line. So that's going to be very valuable for us. Might save us some time. It's also going to be a check to see if we got things right. Now, another thing about limacons, this number is what we call A, and in fact, I'll write down the generic form for limacon, which would be A plus B, r equals A plus B sine theta. In this case, we have A in absolute value is less than B in absolute value, right? 1 is less than 2. So that means we're going to get what we call, I don't know what we call, there's no real name for it. I think of it as kind of like a croissant or a pretzel, something, but we know it's going to look like this. It's kind of got this circular shape, and then it's got this little inner loop on the inside. And that's also very helpful. If you can identify what you're graphing ahead of time, it's going to be much more convenient for you when you do the graph. Okay, let's actually start graphing. Conveniently enough, here's some nice polar graphing paper for us, right? We have all the lines for various angles marked out, and the R values for different values are marked out here, 0.5, 1.0, etc. And as with any YX graph or XY graph, you can always just plot points and then connect the dots. So let's start doing it. Okay, so I'll write the equation again here because I kind of lost it off the top of the screen. Remember that we're graphing r is equal to 1 plus 2 sine of theta. Okay, let's just plug in points. When theta is equal to 0, sine of theta is equal to 0, so r is just going to be equal to 1. When theta is equal to 30, sine of theta is equal to 1/2, so r is 1 plus 1, which is 2. A little trickier when theta is equal to 60, sine of theta is root 3 over 2, so this becomes 1 plus root 3. Now we know that root 3 is about 1.7, so r is going to be roughly, I'll just put a little approximation here, 2.7. We're not looking for a lot of accuracy here. If we really want to do this accurately, we use a computer. Okay, 90 degrees. Sine of 90 degrees is 1. 1 plus 2 is 3, and that's what r is. Why don't we go right ahead now and plot these points? Right, so when theta is equal to 0, I get r is equal to 1. Here we go. It's a nice chunky point right there. When theta is equal to 30 degrees, r is 2. Okay, 30 degrees, r equals 2. There's that point right there. When theta is equal to 60, here's the 60 degree line. R is equal to 2.7. And I'm just going to estimate that. That's right around there, I would say. So there we go. There's a nice point. And then finally, when theta is equal to 90 degrees, I get r is equal to 3. That's all the way up here at the top. Now this is where the symmetry really helps us. Symmetry tells us that this point, if that's on the curve, then I can reflect that across the y-axis and get another point right there. So I'm just going to fill that in. Right there. Now, of course, you can just fill in, you can just plug in 120 degrees and you're going to realize, wait, that's the same thing as when I plugged in 60 degrees. I'm going to get about 2.7. Right, for 150, I'm going to get 2. And for 180, of course, sine of 180 is 0, so I just get r equals 1. And I'm going to plot those other points right now. Right, 150 is right here. Notice that's the reflection of this point, and then the reflection of this point, well, that's right here. And we can see this starting to take shape. I think I have the outer part of the limacon. I don't have the inner loop yet. Okay, so let's keep going. At 210 degrees, sine of theta is minus 1/2, so we get 1 minus 1, which is 0. I'm just going to plot these one at a time, right? So that's at right here. Next. Okay, when theta is 240, okay, sine of 240, well, that has a reference angle of 60 degrees, but it's in the third quadrant. So I get minus root 3 over 2. That's what sine of 240 is. So if I go up here, I get 1 minus root 3, which is about 1 minus 1.7. So I get approximately minus 0.7. Okay, so I'm going to plot that. Now, let's be careful here, right? Normally 240, our dot would be along this line right here, but because r is negative, that says go backwards, right? I'm going to go backwards to r is equal to 0.7, which is right around here where my arrow is. Okay, so that's right around here. There we go. Okay, when theta is equal to 270, sine of 270 is minus 1, so this is 1 minus 2, and I get minus 1. Same thing here. Normally 270 is along this line, and if r equals 1 and theta was 270, it'd be right here, but because r is minus 1, I go backwards, and that's right here is where my point's going to be. So let's plot that right there. And you can see we're forming that inner loop that we know we have. I'm going to use symmetry for this point to tell me that, well, there must be another point right around there. And that actually corresponds to 300. It's approximately minus 0.7. Okay, and then finally at 330, let's see what I get. 330, sine of 330 is minus 1/2, so this gives us 1 minus 1. So we get 0 again, which we've already plotted that point. That point's right here. Okay, we're about done. Time to connect the dots. Here we go. Again, this is probably not going to work out too well because I'm doing this freehand. But let's hope it's not too bad. Okay, not terrible. Maybe you can do better. You probably can do better. Okay, that's it. We just plotted a limacon with a small inner loop. Thanks, everybody.